please take a moment to copy down this example. This example will help you with section 5.6, but it also will be useful for your MATLAB assignment number 4. So let me give you a moment to copy this example down. Very good. Okay, so here we're talking about a spotted owl. A spotted owl in Willow Creek, the Willow Creek, California region. And they actually, show a picture of this spotted owl. Well, I want to be, they show a picture of an owl at the beginning of chapter 5, but this is actually a spotted owl. Now, this owl here, we're not talking about two different species for our stage vector. We can talk about the evolution of a species, of one species, as opposed to the evolution of two species that interact with each other. In this case, we're talking about the evolution of this owl. And the owl has 3 different stages, okay? Juvenile, subadult, and adult. And based on the data of this owl, the biologists created this stage matrix, okay? This stage matrix. And based on that stage matrix A, we want to try to predict, we want to know if the stage matrix A is given by this 3x3 matrix, what does this predict about the spotted owl population for the future? Okay, so we want to know, for instance, is the spotted owl population going to, is it going to survive? Is it going to grow? Is it going to stay stable? Is it going to go to extinct? And, if it grows, we might want to know what's the ratio of the adults to the juveniles to the subadults, for instance, in the future. So one thing that would be helpful, though, is this matrix A, it would be good to be able to interpret these numbers. Okay, it would be nice to be able to have a feel for what these numbers mean. And so on the next page, I'm going to show you that. So everybody has this copied okay? Well, Mikhail, we're going to notice some of the entries. Notice some of the entries in this matrix A are zeros. Okay, so all right, let's go to the next page. Here we are. So I have some of the entries explained. So first of all, why? All right, so one moment here. So after a year, a juvenile is not going to become a juvenile. See this entry here means after 1 year, a juvenile stays a juvenile. That's not going to happen, right? No percentage of juveniles are going to stay juveniles, because after a year, a juvenile becomes a subadult, right? Okay, notice here you have the point 30. Okay, let me just go ahead and clear that. Notice here you have point 30. What does this mean? This means that, okay, a juvenile after a year, hold on, I want things very clear. Notice the point 30 here. Okay, what does that mean? Well, a juvenile after a year can become a subadult. And the point 30 means that 30% of juveniles survive each year to become subadults. Okay, that's how you have to think of that. And a subadult can become an adult with a 71% chance probability, or 71, but we don't want to really think of probabilities here, because you notice that, like in the columns, the entries in each column don't add up to 1. So we don't think of these exactly as probabilities. We think of them as I'm interpreting here. The 0.71 means 71% of subadults survive each year to be counted as adults. That's how you want to think of it. So I guess you could think of it as, if you're a subadult, you have a 71% chance that you're going to become an adult after a year. But I don't like to think exactly as probabilities, because the entries in the columns don't add up to 1. This is not a stochastic matrix where you have probability vectors. Well, it actually will. Mikhail, you make a good comment. Let's look at the last column. So the 0.33, okay, you know, how can you have an adult become a juvenile? Well, if you think, you know, who has the children? It's the adults, right? The adult owls have the children. So if this 0.33 means that for every 100 adults, 33 juveniles are born. So essentially, adults, juveniles can come from adults through the birth process. Now the 0.94 here, what's that mean? That's adults to adults. 0.94, how would we interpret that? Well, each year, how would we interpret that? Each year, that's right, David, good. 94% of adults survive or live. That's how you think of it. Okay, are we all right with this? Are there any questions? Okay, in order to determine what the future is for this spotted owl, what do we need to find for this matrix A here? What do we need to find for the matrix A? What's necessary to find? That's right. Good, Mikhail. Eigenvalues and eigenvectors. So what I did was if we go to MATLAB, find the eigenvalues and eigenvectors. Okay. So what I'm going to do here is the eigenvalues are not going to turn out to be like you're going to get somewhat messy eigenvalues and messy eigenvectors. Okay, so I'm going to just use the eigen command here. So let me show you here. I'm going to go into MATLAB. And again, this will be helpful for your MATLAB assignment number 4, what you're learning here. Okay, so we typed in the matrix A, and now I'm going to do the I of A. Oh my. Oh my. So the matrix D contains the eigenvalues, and the matrix P contains the eigenvectors. So the matrix D, the eigenvalues, well, how many real eigenvalues are there? Three eigenvalues. Okay, here's one. Here's the other. Those appear to be what kind of eigenvalues? Those two eigenvalues. Are they real or complex? The negative 0.0345 plus 0.2617i. Is that a complex eigenvalue or a real eigenvalue? I don't even, to be honest, I don't remember. What format am I using? I guess the regular format, the default format is what I'm using, because I don't need to have it real long. But yeah, the eigenvalues, we have two complex conjugate eigenvalues. And then this eigenvalue here is your real eigenvalue. So don't use the sim command on PD equals eigen of A. Sim command is great if you're going to get nice clean eigenvalues and eigenvectors, but you're not going to get that with this one. So just use the eigen of A. And all right, so even though you have now notice that for the complex eigenvalues, you have complex eigenvectors. Okay, you look at that matrix P, it contains three eigenvectors. The first two are complex conjugate eigenvectors for, hold on here, for this matrix P. Okay, the first two eigenvectors, first two columns are complex conjugate eigenvectors that correspond to your complex eigenvalues. The last eigenvector is real, has real entries, because the last eigenvector here is a real, the last eigenvalue is a real eigenvalue. Okay, I mean, are there any questions on this output? You're going to see this kind of output in MATLAB assignment number 4. Mikhail, the order of outputs of the it is choosing to do the two complex eigenvalues, to list them first, followed by the real eigenvalue. But it could be any order. It depends on what the code's going to produce. It could be any order. But it is kind of nice. It's putting the two complex eigenvalues next to each other in the matrix D. I mean, that's kind of nice, you know. The matrix P contains the eigenvectors, just like section 5.3, the matrix, if A equals P, if A is diagonalizable, A equals the matrix P times the matrix D times P inverse. The matrix D contains the eigenvalues along the diagonal, and the matrix P contains the corresponding eigenvectors. That's why I'm using the letters P and D in this case. Okay, very good, very good. So, okay, we have our eigenvectors, we have our eigenvalues. Now we're ready to assess what the evolution of this system is going to be. Okay, we do the same thing we did with the previous, with you know, the example with the rats and the owls. We do the same thing. We have our eigenvectors and eigenvalues, and now here is the result. And 1.01, by the way, that was 1.0090 rounded to the hundredths place. Okay. So let me just. So 1.001, that's just 1.0090 rounded to the hundredths. The orders don't matter. They do not matter, Mikhail. And you might notice too that when I wrote this out, I specified the you know, the eigenvector, the eigenvalues raised to the kth power, but I did not specify, I did not write down the eigenvectors that MATLAB gave me. And there's a reason for that. Can you imagine what the reason is? Well, not quite that. To determine the evolution of this system, to determine what's going to happen for the spotted owl population for the future, am I going to use, I mean, there are 3 entries here, right, in the solution. Here's entry 1. Here's entry 2. And here's entry 3. Am I going to use, are we going to use all 3 entries? Entry 1, entry 2, entry 3. Which entry do we know which entry, choice 1, 2, or 3, which one do you know isn't very important? Hold on. Let me show this again. Hold on. Let me make this a little. So your number of juvenile, subadult, and adult owls after K years, okay, this is in years, right, is given by this expression. And there are 3 components, to that we use, 3 components. Component 1, component 2, and component 3. Now, which component is important? Component 1, 2, or 3? Which component you know automatically is important in knowing if this population survives or goes extinct? Okay, I'm seeing Mikhail thinks the first component. Why? You're right. Why is that? Cameron agrees. That's right. That's right. The 1.01 here, this value 1.01, okay, is greater than 1. Greater than 1. If you have an eigenvalue greater than 1, what's that going to tell you about the population? Is it going to, what's it going to do? It's going to increase. That's right, Mikhail. And it might increase slowly over time, exponentially slowly over time, but it is going to increase. That means the population is going to survive over time. These 2 other expressions here, these 2 other expressions, okay, if you take this here, this complex number, raise it to the kth power, what is it going to approach as k gets large? That's right. Very good, Mikhail. That's going to approach 0. Same here. This other term here, the last term, same for the third. That's going to approach 0 as k goes to infinity. Okay? That's what's going to happen. There's no way these numbers, as you keep, I mean, they're small. They're less than 1, 0.03, 0.26, they're less than 1. So eventually, if you keep multiplying, you're going to get a complex 0. So that means that only the first term here is relevant to determine the evolution of this owl population. And so as k goes to infinity, the number of juveniles, subadults, and adult owls will equal C1 times 1.01 to the kth power times this eigenvector. Additionally, as k gets large, the number of owls, number of juvenile, subadult, and adult owls in the k plus first year will equal 1.01 times the numbers in the kth year. And that means there's a 1% yearly growth rate, a 1% yearly growth of this population of juveniles, subadults, and adults. That's what that means. Let me give you a moment to copy it. Please let me know if you have any questions. So for the problems that we're dealing with, and in applications with these dynamical systems, you know, the eigenvectors and eigenvalues give you the truth about the evolution of the system. Now, so far, what we've done is we've made use of the eigenvalue, okay, because the 1.01 equals 1 plus 0.01, and that 0.01 gives you the 1% yearly growth, right? But we've not made use of the eigenvector in this problem. Okay, there's these values. Notice the eigenvector values are all positive here in this case. Now, this eigenvector should give us an idea, should help us determine over time what the, I mean, we ought to be able to determine over time, eventually, what percent of the population of these owls are going to be juveniles, what percent of the population over time of these owls will be subadults, and what percent of the population over time of these owls will be adults. I mean, that's an important question. And in order to answer that question, we need to make use of the eigenvector. So what I'm going to do is, in our next class at the beginning, I'm going to continue this example from here and work with the eigenvector to help answer that question. We'll work with the eigenvector. So I'd love to finish this tonight, but we just don't have time. We'll have to wait till Wednesday's class. But are there any questions are there any questions at all regarding this example so far? I mean, who's feeling good so far with section 5.6? Who's feeling good? All right, excellent. Cameron is, Mikhail is. And you'll have enough to do the homework. You have enough information here, what we've covered. You'll be able to do the homework. Please do the homework for Wednesday, okay? Please make sure you get that homework done. It's, this is, all homework's important. This is very, very, very important, right? Okay, excellent, excellent. All right, well, if you're comfortable, I will stop the recording. And very good. And we'll continue this on Wednesday, this example.